Okay, in this show me, we're going to do questions number 6 through 8, because number 5 we aren't worried about right now. Alright, number 6. This one's a little tricky, so I'm going to try to draw this. Alright, so first thing that happens is we know K is equal to 1 Newton divided by a meter. So what happens in the first initial scenario, so I'm going to draw initial. Here we go, this like spring is here, all the way there. Then it's got a little block that's 200 grams. And then there's a string connected to it that's hanging down, and we got 30 gram thing there. Okay? Then in the final scenario, alright, we have same spring, okay? It was stretched 80 centimeters in the first one. Now in the problem, it says the glider is pulled back so that the spring is 80 centimeters of stretch. So that's where I got that. And then it says, how fast will the glider be going after it has traveled 50 centimeters? Well, that means that in the second one, we still have 30 centimeters of stretch left. Because it was at 80 centimeters of stretch, it should still be at 30 centimeters of stretch. So in this one, x should equal 0.8. And in this one, x should equal 0.3. Okay? Now, still have this guy here, 200 grams. And then, now this 30 gram block has moved up 0.5 meters. Alright, so what do we make of this? This is the general setup. Alright, well let's look at what kind of energy do we have in this initial scenario. Alright? Well, in the initial scenario, this guy can't go, this guy here, he can't go any lower because of the spring, right? So we're not worried about him. He has no energy. So this thing we don't worry about. So I'm just going to put a little X through it. All right. There is no kinetic energy here because we've just pulled it back. So the kinetic energy initial is equal to 0. All right. The only thing that we have is this elastic potential energy here. And so elastic potential energy initial is equal to 1/2 times K, which is 1, times 0.8 squared. Alright, that's simple enough. So that's the first scenario. Alright, but now on this second one, weird things start to happen. Alright, on this guy, we had to do work by gravity. And that's going to be equal to the force of gravity on that object times that 0.5 that it lifted. This is essentially energy lost out of the problem. So we'll have to include that in a little bit. This thing now has a kinetic energy. It's going to be equal to 1/2 mv squared. And this spring still has elastic potential energy because it's still at 0.3. So the second little equation, rather than being simple like this, will be fairly complex. So we're going to have the elastic potential energy, 1/2 times 1 times 0.3 squared. Then we're going to have the kinetic energy, 1/2 times 0.2, which would be 200 grams converted into kilograms, times v squared. Obviously, v is what we're looking for because it says how fast will the glider be traveling. And then we've got to work in this over here. Well, force of gravity is equal to mass times 10, so we go 0.03 times 10. But then we have to have it times the height, so 0.5 meters. All right? So basically, what this is the elastic potential energy final. This is the kinetic energy final. And this is the energy lost. Okay? So we have all of this stuff equal to this plain little equation right here because energy initial equals energy final. So I'm going to skip over to this next page and we're just going to copy these things down. So I know that energy initial is equal to 1/2 times 1 times 0.8 squared. So 1/2, well, let me just write out what the full equation is first. We have elastic potential energy initial equals elastic potential energy final plus kinetic energy final plus energy loss. Okay, we know this is 1/2 times 1 times 0.8 squared, and that should equal 1/2 times 1 times 0.3 squared, 1/2 times 1 times 0.3 squared. Again, that's because it was at 0.8, it went in 0.5 meters, which puts it at 0.3, so we didn't use up all the elastic potential energy, plus 1/2 times 0.2 times v squared, plus the energy lost, which was 0.03 times 10 times 0.5. 0.03 times 10 times 0.5. Okay, so there we go. So now if I just multiply everything across, I should get 0.32 equals 0.045 plus 0.1 v squared plus 0.15. Okay, I think that's right. Yeah. Okay, so then I subtract everything that's on a v over to the left side, and I should get 1.25. Okay, 1.25, and that's equal to 0.1 v squared divided by 0.1, and we should get, or rather, I apologize, this should be 0.125. Now divided by 0.1, and we should get 1.25 equals v squared, and square root, and square root, and we get 1.12 meters per second. Okay, back to this first thing real quick. Number 6, the key thing to remember is that this right here, this initial scenario and this final scenario have to be equal. The other key thing to remember, two things on this last part: there is elastic potential energy in the end, check for that, and there is energy loss. Alright, you have to include this in as well. Alright, that's number 6. Alright, number 7, a little bit simpler in a way. Alright, so first thing on number 7 we do is we are looking for 1,000, so we know the mass is equal to 1,000 kilograms. We know that the car, v, is equal to 40 meters per second, but this is the final velocity. The initial velocity is 0 because it starts from rest. We know this happens in 10 seconds, and it asks what is the power of the car. Well, power is equal to work divided by time. Work is equal to force times distance. We have neither. Well, we'll have to figure out distance. So force is equal to mass times acceleration. Alright, we don't have acceleration. Acceleration is equal to Vf minus Vi over t. Well, we do have that, so we can do that real quick. So let's do that. 40 minus 0 over 10 equals 4 meters per second. So just 4 meters per second squared. So that's easy. And now I have a force. So 1,000 times 4 meters per second squared. We should get 4,000 newtons. Okay? Oh, good. So now I have 4,000 newtons. Dadgummit, I still don't have the distance. So, I do have acceleration though. So if you'll remember, d is equal to 1/2 at squared plus vit. And initial velocity is 0. D is equal to 1/2 times 4 times 10 squared. Or d is equal to 200 meters. So I plug that back in up here. And I get the work is equal to, what is that, 80,000? I think that's right. No, 800,000, my bad. 800,000 joules. And then that means that power is equal to work divided by time, so 800,000 divided by 10 is equal to 80,000 watts. And 80,000 watts is your answer. Okay? You may ask, why can't you use that little clever trick I told you about doing the velocity is 40 meters and using that as your distance? It's because the velocity is not constant. You can only do that if the velocity is constant. If you don't know what I'm talking about right now, then ignore me. Alright? Number 8. Number 8, we have to on the first one, how much work is done in the first 10 meters, will work from 0 to 10. We have to take the average force times the distance. Since the force is not constant, it's for those of you that do not have your sheet, it looks like this. Like it's not a constant force over that first 10 meters. It's just a straight line. Okay? So if that's 10 meters, and then till 20 meters, it looks like this. Okay? And that's 5, and that's 0. Alright, so we have to take the average force because you can only do force times distance. Well, we'd have to technically do force times distance at each individual point. If we take the average force, though, we can get it figured out. Well, I think we can all agree that the average force here would be 5 plus 0 divided by 2, which would just be 2.5. So 2.5 times 10 equals the work from 0 to 10 is equal to 25 joules. The second question is, if the object starts from rest, how fast would it be going after 20 meters? Well, this one's a little bit more complicated because now we have to figure out the work between 10 and 20. And that is, well, this one's constant, so it's 5 times another 10 meters. So the work from 10 to 20 is equal to 50 joules, which gives us a total work of 75 joules. And work total equals the change in kinetic energy. So, if we're trying to figure out how fast it's going, we would do 75 equals 1/2 times the mass of the object, which is 2, times v squared. So we get 75 equals v squared, square root, and v is equal to 8.66 meters per second. So we're able to figure that out because we need the work total done on the object. The work total is going to be equal to the work done from 10 to 20 and the work done from 0 to 10 added together, which gives us 75 joules. And then that then is equal to 75 equals 1/2 mv squared. And then we solve for v and get 8.66. So this is questions number 6 through 8.